We're already recording. So welcome everybody to our second session. First, well, I will leave the guys in Warsaw do the whole introduction since it's going to be whole there. But well, yeah, I hope that you enjoyed the first session and thank you for coming to the second one.
Thank you, Ruben. So I think this second session, it's been basically an impact, and our speaker today is Bartosz M Zawora from the University of Warsaw. Please.
Thank you very much. Yes, so as Ruben mentioned, or Nasser actually mentioned last week, our plan is to follow the Mackenzie book, The General Theory of Reading Groupoids and the subgroupoids. And today I will start with groupoids, then I will define Reading Groupoids. I show you a lot of examples, very basic properties, and then I will define the morphism of groupoids, and I will also mention something about the subgroupoids. So yeah, let me recall the definition of a groupoid from last week. Can you see what I'm writing?
Yes, we can. It's clear.
Okay. So a groupoid consists of two sets, each denoted G and M, with maps the source map, which is a map of G to M, parse map, the unit map, which is from M to G, and X, and is the identity X, the inverse is from G to T, such that P and minus 1, and the multiplication which is G takes the H and gives whenever source of G whenever source of H is equal to target of G, and proves right that the kappa is a map from G target B to G, where
Yes, if you move your arms, it usually starts following.
it's a G such that the source of H is equal to the target of G. Okay. So this is the notation that we use. After 1 second. Okay, and these maps are satisfying the following. Source of H, G is the source of G, and target of H is target of H. This kappa is associated, which means that J HG is equal to H G for every arrows that are properly defined, which means that source of J is equal to target of H, and source of H is equal to target of G. The third is the source of the identity X, which is also the target identity for every X element first. And the last one is the two-sided identity, on the source of G is equal to G, and on the target of G is just G. For every element G, and the last one is that for each G.
Sorry to interrupt, but the camera is doing some funny stuff. I don't know if maybe it's the setting or which is well now it's okay. Now it's okay. But the camera was like zooming in and zooming out.
I mean, it zoomed out and then it zoomed in again, but I think the blackboard could be followed most of the time. But you were right, or did someone?
Okay. So let's. Sorry for interrupting.
I will pay attention to the
Yeah, I'm also checking.
okay. So for each G, in G there exists a two-sided inverse, which means that inverse G minus 1 in G such that J minus 1 is the identity on source of G, and G minus 1 is the identity on the target of G, and the target of G minus 1 is the source of G, and source of G minus 1 is equal target of G. And sorry, I shouldn't. So this is the definition of a groupoid that was introduced last week, I think. And to simplify the notation, we denote the groupoid G over M. This is the G space of arrows, M is the base, and this is the notation for a groupoid for now. Okay. So yeah, as about, I mean, elements of G, you can think of them as arrows. Like you can take the G you can think of as arrows that goes from right to left, which is a matter of inversion, with the source X and target Y. G minus 1 is you can think of an arrow from left to right. It's just, I mean, and you can also write the composition, the inverse, and the identity, and so on in terms of arrows, which is also sometimes it's very convenient thinking about the elements of G as arrows. Okay, especially for people that like, draw things. Okay. So then let me present a simple proposition. Okay, so let's G is a groupoid. Let's coordinate in G sort of G is X and target is Y. And then first, if HEG for element HEG with source of H to equal Y and H equals G, then it follows, of course, that H is the identity and X is normally instead from the left to the right. We have something similar for J, G with target is X and DJ is B, then follows that J is the sorry, something some line. Okay, and then for HG with source of A equal G, sorry, Y. And then is the identity A, HG is the identity of X, then it follows that H is equal to -1, and similarly on the right hand for G with target of J and GH is equal to 1 over J. Okay, so this generalization, I mean, it's very easy to prove. That you basically using these identities, and that's all. I mean, it's very fundamental. So I don't problem here. But yeah, this proposition says that basically the inverse is unique in a groupoid. Okay. So more definitions. So this is a groupoid, and then we define Gx is defined as the S-1 of X, and this is the fed fiber Gy over first that's Gy is a D fiber E fiber over 1 M. Yeah, and all indices Gy X is defined as Gx intersected Gy by definition X intersected with phi. Right, so you can think of Gx as arrows. X that goes with a source in X. So these are arrows that start at X and goes whatever. Right, so G Y you can think as arrows that goes to Y, and G function x, you can see this arrows, y, x or that comes from x to y. Okay. And the elements in this gyx is called the vertex. Vertex group. Okay, and one more thing, the set of identities I have, is known, and this is defined as identity M such that this is a clear. Do you have any questions? Okay, if not, I can continue. So now, let's define the groupoid. With smooth manifold structure, on M, on GT and N, such that source map and target map are symmetry submersions. Submersions, the unique mass is smooth. And pouch indication. So now the remark is follows. It says source content target map is our submersions follows that T fibers and S fibers are closed and fed submanifolds. Okay.
Sorry. Yeah, I want to ask the Greek versions.
Oh yeah, that's it. That's a good question, and we'll prove that. I mean, you don't have to ask for it. We'll prove that it's more. Yeah.
I mean, another comment related. Do you have to ask that this the source and target are surjective submersions, or it suffices that you ask that they are smooth maps and that they are surjective submersions, maybe be implied by they're being by the actions of point?
I mean, to ask. I mean, yeah, and having a groupoid, you have to ask for it. Yeah, but I mean, I don't quite understand the question because
Well, basically, I was thinking that there's a categorical definition that is that a Lie groupoid is a groupoid object internal to the category of smooth manifolds, which, besides being pedantic, has the advantage that it's straightforward to generalize it to groupoids on supermanifolds or groupoids on vector bundles or whatever. So I was thinking
You need them to be you need them to be submersions in order to be able to form the pullback of composable arrows. Otherwise, that's not a manifold. So the only reason you need them to be submersions is because you are working in the context of manifolds. But you're right that in a general category, you would just ask that the source and target are maps in the appropriate category and that the pullback of composable arrows exists.
Okay, thanks.
So yeah, before we prove that the inversion is the homomorphism, let me introduce two more definitions. Yes. Left translation. Corresponding to the is LQ and or schema G such that its H and maps to GH and this thing or right translation not this RG and semaphore G such that it's HG. Okay, one definition.
Just a comment.
Yes.
Just a comment. The left translation and the right translation, only groupoid is only defining in the set of composable elements. So you must restrict the definition of the left translation and the right translation. You must restrict to a suitable subset of the Lie groupoid. It's the beta fibers or alpha fibers.
Yes, I agree. I wanted to speed up a little bit, but yes, you're right. H and G has to compose, has to be, has to compose with each other, which means that in this case, the target of H has to be a source of G, and here the source of H has to be the target of G. Yes, that's correct. Yes, I hope it's clear. It's a little bit of misnotation, but yes.
So we will restrict the G there domain to the
Yeah. Yes. Also notational definition for the future. The usual orient. Is that's connected. If each of its F fibers is connected. Right, and we have the same like definition analogous for any property. Like P, we say that any groupoid is as P if the rest fibers has the property P, and same with the targets. I mean T fibers. So this is just an occasional definition. Okay, so composition. So we have the groupoid. Yeah. Now this is the notation for a groupoid. Just to shorten the notation. And the inverse map is a homomorphism. Basically, the proof, follows from inverse function theorem, or the consequences of the inverse function theorem. Okay, so what is the tangent? Tangent bounded to composable arrows instead of composable arrows. This is the y and x. This is in the g and g such that tangent of the source of y is equal. That's good. Okay. Let us take GA in G such that the source of A or target of P Y is in EH ES of H. Right. 1 second. Yeah. Which and X an element by diving into the function map to the multiplication map in a groupoid, is given by R J 1 plus E G H of X. And it's measurable. And goes with this use the picture. Okay, so now let's define map theta, which is from G to G to this is from instead of composable arrows to G, where these are pairs of the arrows such that the target of H is equal to the target of G. Okay, so we take HG and it maps to HG. Okay. Okay, then the idea is to prove that theta is a like that theta is a bijection, immersive bijection. Then the dimensions of G, the set of composable arrows, and G times G over the target map have the same dimensions, which means that the theta is a global diffeomorphism. And then we will define a map, inverse map, using the smooth maps, which means that will mean that the inverse map is smooth, and since the inverse of the inverse map is the inverse map itself, it immediately follows that it's a diffeomorphism. So this is the idea. Okay, so like proving that theta is a bit projection. I mean, it's very simple. So you can verify on your own that is a projection. Okay. And the inverse of theta of I k is equal I minus 1. So now we have to prove that theta planes is theta is an inverse. Okay, so I assume that theta on y x is 0, 0. Now let me introduce the two projections P1 and I2, which in general, I mean, it's from P times G to G such that HG, and it projects like on the first component with respect to the composition. So it is G and G D mass H. So now, since by definition of theta, since it doesn't change the first component, one has that P2 and theta composed with P2 is equal P2, and from this follows that y is equal 0. Here. So now we have to prove that x is also 0, but like the Leibniz rule, the triangles, and by definition of theta, where the second component of theta map is the composition of arrows, and by Leibniz rule of the kappa map, it also follows that x is equal 0. Okay, so theta is an immersion. So now, since it's immersion, let me erase it. Since theta is a bijection and is an immersion, and the dimension of is equal to the dimension of G over times G, it follows that theta is the diffeomorphism. Okay. So theta is a diffeomorphism, then define a map mu from G to G and G over target as follows. This takes H and maps to H and identity over the target of H. And then the composition of mu with theta minus 1 with U1 on H. By definition, this is P1 composed minus 1 on H. Identity of target of H. Then theta minus 1 is defined. I erase it, but this is just so one remains, and this is H and H minus 1. And the projection of the first factor with respect to the composition is H minus 1. So the conclusion is that this is the inverse map. So now this is the inverse map. So it's this the composition of smooth maps. So inverse is smooth map, and since the inverse of a inverse map is the inverse map itself, it follows that this is the diffeomorphism. Which finishes the property. Right. Do you have any questions? If not, as we continue, with the remark, the unit map the unit map is smooth, or is smooth in immersion. And because the target composed with mu is the identity of M in the same way. And same with source. Now, using tangent filter to this, we get the limit of the immersion. Okay. So now let me show you some example of groupoids and Reading Groupoids. So now there's the part with a lot of examples. In most of you probably know, but So first example is a Lie group. And every Lie group can be considered as a Lie groupoid with a unique unit, which means that this is the Lie group over the single point. So this Lie groupoid gives a Lie group G. Okay, second example is manifold. So any manifold can be considered as a groupoid on M with trivial maps for the identity of M and the same with target. Okay, so this is also a groupoid. Yeah, I think, we'll assume that manifolds are finite dimensional, of course, and most of the time Hausdorff. Not every time, because I hope when we get to foliations, there naturally appears Lie groupoids that are not Hausdorff. But for now, we assume that all manifolds are Hausdorff. Okay, so next example is a groupoid. So groupoid, groupoid, M times M on M, and the maps are defined spokes. The arrows are just a pair of points. Times M. The source of y x is x. Target of y x is s y. The unit is just x, and this is the identity and the inverse map of y x. This x y, and the composition kappa is defined when the source when the source of this is equal to target of this, which is y in this case, and this is just the z x. Okay. And here the observation is that the vertex and the result of the x is trivial. Okay. Next example. Trivial groupoid. And it's manifold of course, since G is a group. And then the groupoid is G times M over M. So instead of comparison of triangles, so the source of y g x is equal to x, target of y g x. is equal y. The unit it's x in x, where E is the neutral element in E group, and the composition H Q. Sorry, x or y is y is Q. Let's see the composition. The source of this is equal part of this, so we can compose it, and this is G H E X. Okay, and of course the inverse is y G X. Inverse of this is x G minus 1 and 1. Next example. Submersion groupoid based on Fourier submersion of MQ are manifold, Fourier submersion, and then we go for it over Q, I over M, and this is the structure of the groupoid here is like the structure of a pair groupoid. Structure of a pair groupoid restricted to this, which maybe write this means is y x is such that the x equal to 4. So the next example is the example of action groupoids, which both are actually introduced last week. So yeah, we have a little we have a little action and little action, and then G times M over M becomes a groupoid with source of the arrows. The arrows are the first G X in Q, and then the source of the X is just the point X, the projection, and the target of the X gives the action of G on X. GX. The unit of X is of course the neutral element, and the point X, the inverse of G X is G minus 1 GX, and the composition G2 1 say G1x is G2 G1 x whenever if y is equal to G1. Okay, so this is the condition for these arrows to be composable. Okay, introduction groupoid is denoted by this, and of course the xf is the isotropic subgroup point x. Okay. You have any questions? If not, let's consider next example, the specific case of the actual groupoid. Just to get familiar with these groupoids. Yeah, one, this one, is an action of C. Okay. And this gives, so this shows that this gives the groupoid. So, and this is basically the cylinder. So, and the base manifold could be set for b equals 0, and so this is this one. And what are the source is the tree in the target of the this. Right, so let us see what are the S fibers and P fibers of this groupoid. So what are the S fibers for some C? So these are the colors. So in this case, S fibers are just straight lines. This is X, Z story here. So these are the S fibers, right? Since the S is just a projection of the buffer. So what are the P fibers? So P fibers, as you can imagine, are the helices. So this is not C prime. So what are the fibers of C prime? These are all curves PC, right, such that PC is equal to 1, which means that this is like the helix list of this sort. Yes, so this is here to E for 1, this is for 1 half, and same with the minus. Yeah. So what is the R equals S1 VV? I mean, it goes at the point C for all integers. It is C times So now is another example, Oscar's favorite example, and fundamental groupoid. So let P of M be the set of homomorphic classes gamma square brackets where gamma is a continuous part from interval 0, 1 to n. Derived at these points gamma 1, 0, right? And then we have a groupoid structure where the source node is gamma 0, paradigm is gamma 1 over the unit prime. That's x. It gives the gamma x, where gamma x is constant. X. The composition alpha is just a natural concatenation of mass. So the gamma is just the gamma. So I guess that you know how it works in composition here.
And it is because in the literature sometimes this is presented just as an algebraic point, not as a Lie groupoid, but I guess it follows as long as the paths are taken as smooth paths, it should follow easily that is. Yeah.
Yeah, the inverse is just the reverse path, right? So it's let's note that with that method. It starts at the path from gamma 1 to gamma 0. And of course the gamma reserves E and X is just a fundamental group. That's X. More examples. Let E Gaussian be a vector. This is the example of frame groupoid. Can we modify that also follows vector isomorphism and vector space isomorphism. From X to UI. Okay, then it's a Reading Groupoid in this force. So force X target is Y. Yeah, the multiplication is just the composition of maps. The unit gives the identity EX and the composition of maps. And the inverse, of course, since these are isomorphic, the inverse is just the inverse of. So this is the frame group for it. So another example is the groupoid. So let's find the local isomorphism. For an open set, open set 1 for M. For X, we have the one jet and the one jet at X of phi. And J1, which is the equivalence process of the one jet, and gives a groupoid structure with a baseline for M, where the source X1 is just X target 1 X5 is phi of X. The composition on X side J1 X I, and this is J1 X side also with phi. The inverse is just the inverse map. So this is the jet groupoid. Okay. Yes, so there is 3 more examples. Another example. How much time do we have?
Like 4 and 6.
It's engageable for you. So let me be a print for the bundle. Okay, and let G acts from right, the one on the right. With U1, or U2, U1, U2. So equal facts. Well, sorry. Okay. Yeah, and let the U1 denotes the equivalence clusters in E and E portion by E portion G. Value G. Okay, and then E and E divided by G is groupoid over M. Okay, so how maps look like the source is E of U1, target U1 is E of U2. The unit map of X gives the equivalence classes of right. For the preimage of -1 of X. Okay, and the composition map is given following you I mean I'm simplifying things because in general these elements don't have to be the same, but have to belong to the same orbit. But you can always find a representative in orbit such that these are equal for composable arrows. Sorry, this is 1, this is 3, U1. And this groupoid is called gauge groupoid. Okay. Similar example. The GB group with the algebra G, and then E star D over G star is a groupoid where the target of theta takes from theta in the RG, right? So for such element, target of theta is called theta composed with RG, source of theta is theta composed with LG. In composition, the composition is even for such elements theta take the same values, which means that you have the protons. Just this as the R -1, and this is well defined for such theta phi So this is equal and RCT. The unit map take the element in G star and gives the element at T E star to G, and then inverse. Just get that right down. Inverse. Yes, that involves LG reaching RG. And the last example I want to show you.
Sorry, just a question. Yeah, the gate group point, like you just used that there is a foliation, right? It's just the group didn't delay any special order or
Oh, we want the question spaces, manifolds. I mean, this is a Reading Groupoid. This is the principle. It's a legal group. It's a group.
the first of all.
Once again,
The principle is important.
well, we use the projection here, so we want to have a bundle structure.
Yeah, I guess his point is that it could be a sub-fiber bundle.
Yeah. Okay. The last example was very short. We have a little poly. We just apply the tangent or get tangent groupoid. Basically, it's and this is called tangent groupoid. We have the source in here, the tangent manifold source in here. The target map here is the tangent manifold target map in here, and the same for multiplication, inverse multiplication, and so on. Okay. So now let me introduce the notion of morphism of groupoids. So we have two groupoids. Morphism of these groupoids. The curve maps such that all journals are used. Anyway, where S prime is the source, prime groupoid is the target. Target. And this one will get It's all these three paragraphs. If the small f is the identity over m, we say that we have a morphism of groupoids over base manifold, or base preserving morphism. And the pair f and f is a morphism of groupoids if the maps f and f are smooth. Actually, it's sufficient to assume that f is smooth and capital F, then the smoothness is small f that comes from the smoothness of the capital F.
So relating it with your previous example, the tangent factor.
Yeah, exactly. I mean, in terms of, because the groupoid can be also defined using the, let me say, the category language, as Oscar mentioned previously. So this morphism can be also described via functors, basically.
Yeah, you're saying that the tangent is the morphism.
For instances. Exactly. Okay, so now we have a very simple proposition. There's the legal point morphism, or it's just hopefully. Then, or that's all as as cheating or this is the whole of cheating lines or positive each. Okay, so definition that the morphism of groupoids is an isomorphism it's not smooth, but sorry, the diffeomorphism. So and since f is the diffeomorphism, then it follows that the small f is also diffeomorphism. Okay, so let me show you some examples. For the groupoids map size under the target and source from G n times n is a G, like it is G source of G. There's a groupoid morphism between this groupoid and per groupoid. And the map chi is called the anchor. our transfer of G. Next to this is more easy. Um, here, another example is that the action groupoid, where the action of G on G star is given by the adjoint action is -1, G -1 star. Then the left realization of G minus G star to G star G define composed with -1 is an isomorphism of groupoids, actually groupoid, and groupoid from this example is the star G on G star, where it's just a matter of it's simple computation, but all the diagrams commute in the definition of this isomorphism of groupoids. Okay. And of course, also as you mentioned, another example is that for any example, this should be the projection from the bundle of sheets, and in the end, the projection of the unbundle gives the groupoid morphism between each and yeah. Okay, so at the end, let me introduce the definition of a subgroupoid, and then just subgroupoid. I will finish here. So the definition is the groupoid then these subgroupoid over M is groupoid d prime over M prime, where the immersion and to M such that the error is way more. And then we say that stuff is embedded if G prime and M prime are embedded of manifold of G and M, and then a groupoid G prime and prime is wide if M equals M prime and E of M is incorporated over M. So it's basically for sake. Thank you very much for your attention, and I hope you didn't get bored or with all these examples.
Thank you, Bartosz. Comments, questions?
Maybe a quick question from Madrid. In the example of the fundamental groupoid, maybe this was already one question by Asier, but I did not fully understand because. But just in case, to make sure, in the fundamental groupoid, is this truly a Lie groupoid? Like the class of holomotopy, like the set of homotopy classes?
No, it's not a groupoid. It's just a groupoid.
Okay.
No, that's what I said. Yeah. I think maybe you assume that you take the curves to be smooth. That is like homotopy classes, not the whole curves, but the smooth curves.
Yeah, exactly.
Maybe there's other technical detail that you.
Yeah.
Okay.
What if there's a manifold structure on the space, the total space?
That's true.
Okay, thanks.
Sorry, I haven't got this structure. What was the TGTM groupoid? Was it tangent groupoid?
Yeah.
So how was it defined?
You mean
Yeah.
And it's source in here. In here is the tangent map of the source.
Okay.
Right, because it comes from the legal body. So you have source map. So you have the source map, the tangent map, of the source. The same with all maps. That comes from the. Sorry.
Just for the record, I'm not sure if the chat is visible in the recording. David Iglesias Ponte said that to the previous question that if the original set then the original set M is a manifold if it's linkable. Yeah. If the Lie set M is a manifold, then it is a Lie groupoid.
Yeah, I don't know if you can hear me.
Yes.
Okay, yeah. Now I think I had some problem with the audio. Yeah, I think if the original manifold, yeah, the set is a manifold, and I think you have to consider, of course, smooth curves, and then smooth homotopes and so on. Then I think it's a Lie groupoid.
Just a comment, but if you have a smooth manifold and you define the fundamental group with a smooth curves, then the fundamental group coincide with the fundamental group if you define this group with the continuous curves. It's just the same.
Isn't
Right?
it the case that every homotopy class has a smooth representative or something like that? Yeah.
Yeah, sure.
Yeah, by approximation. Yeah.
Yeah, by approximation, yes.
Thank you.
I think, if I'm not wrong, there is a book that is on the internet by Ronald Brown talking about, in general, groupoids. I mean, he developed all the theory of a fundamental groupoid, covering groupoids, and so on. I think it's a nice place to, I mean, if you really want to look at that direction. I mean, his interest when he wrote the book, if I'm not wrong, was to develop all the theory of fundamental groups, but using groupoids. So for the people interested in even in just in the topological setting, it's a nice reference to look at.
Okay, thanks.
You're welcome.
More comments, questions? Well, just a brief comment to define this anchor so that for every Lie groupoid we have this morphism to the product groupoid. So I guess if this morphism is an isomorphism, basically means that the groupoid is trivial, like when in the case of vector bundles when they are parallel cycle.
Yes. Yes.
Thanks to you, Juan Carlos. Are there any more comments or questions? If not, I guess we can close the session for today.
Maybe just a brief comment before. Wait, let me put the camera just to say. Yes, okay. Maybe just a brief comment. Okay. Oh no, yes. The video, the first video had a bit of poor quality. I think we have already solved that. Hopefully, we will see in the next video. But yeah, just for you to know that from now on, the quality will be better of the videos. It was a problem with Zoom. But I just wanted to mention that. Sorry. I don't know if you want to mention anything else, Asier or Bartosz.
Well, yeah, that you will give the next talk, right?
Yeah. I will give.
The next talk will be given by Ruben from ICEMAT. And the week after, we will not have a session because there's a conference that several of us will be attending. All this information is also on the website of the next sessions. And I think that's all.
Okay.
Thank you.
Then I think I will post stop the recording.